Welcome back, everyone, and thank you for joining me today. Please take your seats. Today, we are opening a brand new and incredibly exciting chapter in our Watchmaking Theory course, Chapter 8, Automatic Winding Mechanisms. If our previous modules laid the groundwork for manual gear trains and escapements, this chapter is where we introduce true autonomy into the machine. Over the course of this lecture, which is divided into 4 comprehensive parts, we are going to explore one of the most elegant innovations in the entire history of mechanical watchmaking. We will be looking at how we can capture the chaotic, everyday kinetic motion of a human being's wrist and transform it into highly regulated, continuous mechanical potential energy. Here in Part 1, we will begin by tracing the historical evolution of this technology. We'll look at the brilliant pioneers of the 18th century who first dreamed of a watch that didn't need a key to be wound. From there, we will transition into the modern era, dissecting the precise anatomy of the oscillating mass, commonly known as the rotor. We'll look at the materials, the structural requirements, and the fundamental physics that allow this heavy piece of metal to breathe life into the movement. So, get comfortable, direct your attention to the blueprint on the screen, and let's dive into the world of automatic winding. Before we look at the historical progression, we need to establish exactly what an automatic winding mechanism is fundamentally trying to achieve. Take a look at the conceptual flow diagram on the screen. It represents a continuous, self-sustaining mechanical loop. On the far left, we have the kinetic input. This is the oscillating mass, or the rotor. Its sole purpose is to react to gravity and the natural, multidirectional movements of the wearer's wrist or body. It takes that chaotic motion and converts it into rotational force. This force then moves into the second block, the gear train. This isn't the train that drives the hands, this is a dedicated reduction train designed to multiply the torque generated by the rotor. Next, we move to the ratchet, which acts as a mechanical diode. It ensures that the energy only flows in one direction, preventing the system from unwinding itself. Finally, on the right, we reach the ultimate destination, potential energy. The force compresses the mainspring inside the barrel. Why does this matter? Beyond the obvious convenience of eliminating the need for daily manual winding, an automatic system keeps the mainspring at a near constant state of maximum tension. This provides the escapement with a highly consistent isometric torque curve, which dramatically improves the chronometric accuracy of the timepiece. To truly appreciate where we are today, we must look back to where it all began. The year is 1770. And the genius who started this revolution is Abraham-Louis Perrelet, a watchmaker born in Lulacal, Switzerland. He is widely credited with inventing the very first documented automatic winding mechanism. Now, you have to remember the context of the era. The portable timepiece of the 1770s was the pocket watch. Therefore, the platform Perrelet was working with rested vertically in a gentleman's waistcoat pocket. Because of this orientation, the input method he designed had to harvest vertical body oscillation, the up and down motion of walking or riding a horse. Look at the image of the historical movement on the left. The energy path relied on a weighted lever that bounced up and down. This vertical motion was captured, transferred through an oscillating lever, and used to tension the mainspring. At the time, these miraculous devices were known in French as montres perpetuelles, meaning perpetual watches, or assicaces, which translates to shaking watches. The key takeaway here is that Perrelet successfully proved the concept of harvesting human motion, but he was strictly limited by the vertical orientation of the pocket watch. Let's take a much closer look at the anatomy of Perrelet's original lever mechanism. Look at the schematic on the screen. It is a masterpiece of 18th century microengineering, utilizing 7 interdependent parts to form a complete, single-direction winding system. Component number 1 is the oscillating mass itself. As the wearer walks, this mass descends under the pull of gravity to drive the system. Connected to it is component 2, the winding spring, which acts as the flexible transmission arm, transferring the downward motion from the mass to component 3, the winding wheel. This wheel acts as the first stage of the reduction train. To ensure the system actually stores power and doesn't just bounce back and forth, we have component 4, the stop spring. This acts as a one-way lock, preventing the winding wheel from reversing. Component 5 is the limit pin, a physical barrier that restricts the maximum downward travel of the heavy mass. Component 6 is a crucial return spring, which pushes the mass back up to its starting position after each downward stroke. Finally, component 7 is an ingenious safety pin. When the mainspring is fully wound, this pin lifts the stop spring, effectively disconnecting the winding mechanism to prevent the mainspring from snapping. Now, let's put this machine in motion and trace the step-by-step kinematic cycle of the Perrelet mechanism. Follow the colored arrows on the diagram. It is entirely passive, the wearer does nothing but walk. In step 1, the wearer takes a step. The body descends, and the oscillating mass, item 1, swings downward due to inertia. In step 2, this downward mass physically drives the winding spring, item 2, which engages the teeth of the winding wheel, item 3. Moving to step 3, as the winding wheel turns forward, the stop spring, item 4, clicks over the teeth, locking against any reverse rotation. It establishes a one-way limit. In step 4, the rotation of the winding wheel transmits its force through the reduction gear train, all the way to the barrel arbor, tensioning the mainspring. In step 5, the mass eventually hits the limit pin, item 5, stopping its travel. The return spring, item 6, then takes over, pushing the mass back up to the top, ready for the next step. Finally, in step 6, if the watch reaches full tension, pin 7 raises the stop spring, bypassing the winding force to prevent breakage. It is a continuous, self-regulating, passive mechanical loop. As brilliant as Perrelet's lever system was, it suffered from several severe mechanical and practical drawbacks that prevented it from becoming a mainstream success. Let's look at the diagnostic matrix on the right to understand why it failed commercially. First, there was an acoustic issue. Every time the heavy mass reached the end of its travel, it violently struck the limit pins. This produced a noticeable, rhythmic knocking noise that was highly disturbing and unrefined for the wealthy gentleman wearing them. Second, this led directly to tribological wear. The repeated shock impacts of metal hammering against metal caused accelerated deterioration of the fragile 18th century components. Third, there was a massive efficiency loss. Winding only occurred in one downward direction, the return stroke, pushed by the spring, wasted potential energy. But the ultimate flaw was a kinematic mismatch. A pocket watch sits horizontally in a pocket, moving up and down. A horizontal oscillating mass rotating on a central pivot simply does not receive enough lateral impulse in a static pocket to wind effectively. As a historical result, total production of automatic pocket watches in the 18th and 19th centuries amounted to only a few hundred pieces. It was commercially negligible. Realizing the limitations of the bouncing lever, Perrelet actually developed an advanced rotor version, which you can see in the photograph here. This is an incredibly rare artifact, representing a massive conceptual leap. Notice the architecture. Instead of a lever swinging from an offset point, we now have a central pivot. The rotor is mounted squarely at the center of the movement. Furthermore, it allows for full 360-degree rotation. There are no travel limits, no stop pins, and therefore, no knocking noise. It resulted in silent, continuous rotation. It also featured bidirectional kinematics. Using two ratchet wheels, it could actually wind the mainspring regardless of which way the rotor spun. This architecture is the direct conceptual precursor to almost every modern automatic wristwatch movement in existence today. However, it had a fatal flaw at the time. Pocket watch wearers still moved mostly vertically. A centrally pivoted, horizontal rotor receives virtually zero effective rotational impulse while sitting upright in a static pocket. The physics simply didn't match the human behavior. Because of this, the concept was abandoned, and only about 2 surviving examples of this pocket watch exist today. The wristwatch had to be invented before this rotor could shine. The paradigm shifted entirely in the early 20th century with the transition from the pocket watch to the wristwatch. This was the true revolution for automatic winding, spearheaded by a British watchmaker named John Harwood in 1923. Look at the diagram showing the wrist rotation. The physics of human motion changed completely. When a watch is strapped to the wrist, the natural pronation and supination of the arm, the twisting and turning, creates rotational energy. It is no longer just purely vertical bouncing. This made the centrally pivoted oscillating mass genuinely practical for the first time. Harwood capitalized on this and patented the first commercially successful automatic wristwatch. Let's look at the mechanism specs. He used a centrally pivoted oscillating mass located at the center of the movement. However, it was not a full 360-degree rotor. It was a bumper style. The mass oscillated through a restricted arc of approximately 130 degrees. To solve Perrelet's noise and wear issues, Harwood installed helical bumper springs at each extreme to absorb the impact, replacing the old rigid pins. Finally, the system utilized unidirectional automatic winding. Harwood proved that an automatic watch could survive on the wrist. Let's take a closer look at the actual Harwood watch to appreciate its unique design features. It was a radical departure from traditional watchmaking. On the left, we see the bumper architecture exposed. You can clearly see the heavy mass restricted to its 130-degree arc. At the edges of that arc, you can see the tiny coil springs, or boudoirs. These shock absorbers soaked up the kinetic impact of the mass instead of letting it slam into rigid pins. This made the watch dramatically quieter and drastically reduced wear on the pivots. While it was a single-direction winding mechanism, which is simpler and requires fewer parts, the 130-degree limitation meant it only partially utilized the full rotational potential of the wrist. But look at the image on the right. This is the crownless interface. Harwood was so confident in his automatic winding system that he eliminated the manual winding crown entirely. This was unprecedented. To set the time, the wearer physically gripped and turned the rotating fluted bezel, the lunette tournante, which moved the hands via an internal clutch. Eliminating the crown removed a major point of dust and water ingress, proving that the automatic wristwatch could be a robust, self-sufficient machine. From the introduction of Harwood's bumper in the 1920s to the 1950s, the automatic wristwatch underwent a period of rapid, intense evolution. We can trace this evolution across three main benchmarks: kinematics, architecture, and material science. Looking at the timeline on the screen. In 1930, we have the stacked bumper. The mechanism was essentially bolted on top of a manual movement, making the watch very thick. In terms of kinematics, engineers soon introduced bidirectional winding, harvesting energy from both directions of the rotor's swing to maximize efficiency. By 1940, we see the semi-integrated phase. Engineers began carving out space in the base caliber to sink the automatic module lower, drastically reducing total movement thickness. Finally, by 1950, we arrive at the flush 360-degree rotor. Material science gave us denser, heavier alloys. This allowed the mass to be smaller and flatter without sacrificing rotational inertia. The bumpers were eliminated, allowing the rotor to spin a full 360 degrees silently and continuously. By 1950, this full rotation, centrally pivoted rotor flush with the movement became the definitive mid-century standard, and it is the architecture we still use today. Now that we understand the history, let's dive into the core engineering. How does the oscillating mass actually operate? Let's look at the operating principle of the modern rotor. The energy source is, of course, the wearer's multidirectional, highly erratic rotational wrist movements. The automatic module itself is typically mounted directly above the base movement, on what we call the bridge's side, or côté pons. Follow the transmission path indicated by the arrows in the diagram. The heavy rotor rotates 360 degrees around a central pivot. This high-speed, low-torque rotation is fed directly into a reduction gear train, or rouage de demultiplication. This train mathematically converts the speed into massive torque. This torque is applied to the ratchet wheel, which turns the barrel arbor, thereby tensioning the mainspring. Therefore, any automatic mechanism can be broken down into two key subsystems: System A, the oscillating mass assembly itself, which captures the kinetic energy, and System B, the winding gear train equipped with direction control, which processes and routes that energy. We will examine both of these systems in painstaking detail. As we saw in the historical overview, oscillating masses generally fall into two distinct types. Here is Type A, the limited rotation oscillating mass, commonly known as a bumper. Look at the specification matrix. The angular range of this mass is strictly restricted, typically to an arc of about 120 degrees. It pivots at the movement center, but it cannot spin freely. To prevent catastrophic damage when the heavy mass reaches the end of its travel limiters in the form of helical coil shock absorbing springs are installed at each end of the arc. Furthermore, these older bumper systems almost exclusively utilize unidirectional winding. What are the engineering trade-offs here? The pros are that it is a mechanically simpler mechanism, requiring fewer components, which lowers manufacturing costs. The cons, however, are significant. Energy capture is severely limited because the mass hits a wall and stops. Furthermore, the physical bumper springs add vertical bulk to the movement, and only a fraction of the wrist's full rotational motion is actually utilized. While mostly obsolete in modern mass production, you will still see this architecture in mid-20th century vintage restorations and occasionally in highly specialized modern micro-rotors. Moving to the modern standard, we have Type B, the full rotation oscillating mass, universally referred to simply as the rotor. Looking at the matrix, the definition is clear: the oscillating mass rotates freely through an unlimited 360-degree plane. There are absolutely zero restrictions, zero bumpers, and no travel stops. This results in a continuous, incredibly silent rotation. The energy capture of the Type B system is vastly superior. Every single wrist movement, regardless of its direction or amplitude, contributes to spinning the rotor and generating power. Depending on the gear train design behind it, this rotor can be configured for either single direction or bidirectional winding. However, there is one massive prerequisite feature required for a 360-degree rotor. Because it never hits a physical stop, it will continue to wind the mainspring endlessly as long as the watch is worn. To prevent the mainspring from snapping under infinite tension, the barrel must be equipped with a sliding bridle, a slipping clutch, which we will analyze fully in section 8.4. Today, the full rotation rotor is the undisputed standard architecture in virtually all quality automatic watches. Let's talk about how this automatic module is actually integrated into the watch movement. We generally classify this into two distinct integration architectures, the stacked era and the integrated era. Look at the cross-section on the left representing the stacked era. In early automatic implementations, watchmakers essentially took an existing, fully functional manual wind caliber and bolted an automatic winding module directly on top of it. You can see the distinct layers. The manual gear train is below, and the automatic rotor and its heavy gears sit high above. This resulted in watches that were extremely thick and bulbous, often derisively referred to as bubblebacks. On the right, we see the modern integrated era. The pursuit of elegance and wearability drove horological engineers to completely redesign the base caliber from the ground up. They engineered the main plate and bridges specifically to house the automatic reduction gear train within the exact same horizontal plane as the manual gears. The rotor is recessed so it sits nearly flush. This eliminates the stacked bulk, resulting in the slim, elegant profiles we expect from luxury automatic watches today. Before we move deeper into the rotor's physics, I need to preview a critical safety mechanism, the sliding bridle, or slipping clutch. Here is the unrestricted rotation problem. As we established, a 360-degree rotor never hits a physical stop. It will continue to violently force torque into the gear train as long as the watch is on a moving wrist. The consequence of this is fatal. Without intervention, this continuous, infinite winding force would either snap the steel mainspring in half, or shear the microscopic teeth right off the reduction gears. The solution to this paradox is the sliding bridle, or bride glissant. Look at the diagram of the barrel. Instead of the outer end of the mainspring hooking rigidly into the barrel wall, it is attached to a stiff, curved piece of spring steel, the bridle. This bridle presses outward against the smooth inner wall of the barrel using friction. When the mainspring reaches its maximum safe tension, the rotational pull overcomes the outward friction, and the bridle simply slides, or slips, along the inner wall, safely venting the excess energy. We will do a full mathematical analysis of this slip later, but remember, unlimited harvesting demands a continuous pressure relief valve. Now, let's dissect the physical anatomy of the oscillating mass itself. A modern rotor is not just a single chunk of metal, it is a highly engineered, two-part system designed to maximize gravitational pull while surviving brutal shocks. Look at part 1, the mass support, also known as the rotor arm or support de la masse oscillant. This is the inner structural backbone that connects the delicate central pivot to the heavy outer rim. It is typically machined from brass or mailchort, which is nickel-silver. The most crucial property of this arm is not rigidity, but engineered, controlled elasticity, which we will explore in the next slide. Attached to the periphery is part 2, the heavy sector, or secteur lourd. This is the crescent-shaped outer rim. Its sole function is to provide the massive gravitational torque required to drive rotation. Therefore, its primary property must be extreme density. The goal is to maximize the moment of inertia by packing the heaviest possible material into the absolute smallest physical volume at the furthest edge of the rotation. The rotor is a beautiful marriage of a compliant structural arm and a dense gravitational driver. I mentioned that the mass support arm must be elastic. Let's explore the physics of shock defense and why a rigid rotor is a dead rotor. The threat is constant. Wristwatches experience severe, frequent shocks, massive g-forces from being dropped on a desk or hitting a doorframe. Look at the red arrow on the diagram representing an impact. If the mass support arm was completely thick and rigid, it would transmit 100% of that kinetic shock energy directly into the microscopic central pivot bearing. The result? Shattered ruby jewels and permanently bent axles. The watch would instantly stop. The elastic solution is brilliant. Watchmakers machine the support arm to be exceptionally thin in specific areas. When a shock occurs, the support arm physically deflects and bends, acting exactly like a leaf spring in a car's suspension. It absorbs the peak force of the impact, flexing downward, before that energy can reach the delicate bearing. This is why brass and mailchort are used, they provide the exact required elastic modulus. It's not a material compromise, it is a highly deliberate, engineered shock absorption mechanism validated through extreme drop testing. Because the rotor arm is flexing and bouncing, while the heavy sector is violently pulling, the joint between these two different metals is subjected to immense stress. How do we attach the heavy sector to the elastic arm without it shaking loose over millions of cycles? There are three primary methods used in the industry. Method 1 is riveting. Here, metal pins are driven through both components and cold-formed, or crushed, to bind them. It is exceptionally highly vibration-resistant and permanent. Method 2 is setting or crimping. Look closely at the cross-section. A precise groove is machined into the heavy sector. The edge of the elastic arm is placed inside, and the heavy metal is mechanically deformed, or crushed down, to bite into the arm. Method 3 is screwing. This utilizes microscopic threaded screws to bind the plates. It allows a watchmaker to actually remove and replace the heavy sector during a service, but it requires exacting torque specifications to ensure the screws don't back out from rotational vibration. In the highest echelons of horology, you might also see advanced welding or aerospace-grade adhesive bonding. Regardless of the method, this joint cannot develop even a micron of play. Let's talk about the material science behind the heavy sector. The entire game here is maximizing density versus volume. Look at the specific gravity chart on the left. The historical standard was cast lead, with a density of 11.3 grams per cubic centimeter. It was cheap and heavy, but lead is toxic, too soft, and crucially, it required a massive physical volume to generate enough weight, resulting in very thick watches. Lead is completely obsolete today. The modern standard is sintered tungsten alloys, coming in around 19.0 grams per cubic centimeter. This is the optimal engineering choice. Tungsten powder is sintered in a copper-nickel matrix. This extreme density allows engineers to maximize the heavy mass within a microscopic physical envelope at a moderate cost. Finally, in the realm of horology, we see 18-karat gold or platinum and iridium alloys, pushing past 21 grams per cubic centimeter. While prestigious, this isn't just for show. The extreme density of platinum is an absolute engineering requirement when designing ultra-slim watches or micro-rotors, where physical space is virtually non-existent. The density imperative is simple: higher density directly yields a greater moment of inertia for the exact same physical volume. Let's synthesize what we've covered in Set 1 before we bridge into the heavy physics of Set 2. We traced the history from Perrelet's 1770 vertical lever, through Harwood's 1923 bumper, arriving at the ultimate 1950s standard, the universal 360-degree, flush-integrated rotor. We dissected the rotor's anatomy, understanding it as a bipartite construction that elegantly combines a flexible, shock-absorbing elastic arm with an ultradense, gravitational heavy sector. The entire history of automatic winding has been a story of perfectly matching the mechanical architecture to the environmental motion of the human wrist. This structural foundation prepares us for Set 2, the physics of harvesting. Coming up, we are going to look at the strict mathematics of kinematics, specifically the moment of inertia equation, I equals the integral of r squared dm. We will explore tribology, analyzing how rotor suspensions evolved from high-friction locking clips to near-zero friction ball bearings. Finally, we will trace the force through the gear reduction train, understanding how a 1:180 ratio mathematically multiplies human motion into mainspring torque. Let's turn the page to Set 2. Welcome to Part 2 of our module on automatic winding mechanisms. Having established the history and the physical anatomy of the rotor, we are now going to shift our focus entirely to the deep engineering and physics of rotational energy harvesting. This module focuses on 4 key learning objectives. First, kinematics. We will dissect the mathematical optimization of the moment of inertia, or I, in rotor design, and see how shape dictates power. Second, tribology. We will trace the evolution of rotor suspension systems, examining how engineers battled parasitic friction to create the modern ball-bearing nexus. Third, force multiplication. We will map the precise 1 to 110, or up to 1 to 180 gear reduction train that magically transforms chaotic, high-speed wrist flicks into the massive, slow torque required to compress a steel mainspring. Finally, efficiency. We will uncover the mechanical rationale behind single-direction winding. Take a look at the blueprint on the screen. The structural foundation is set. We must now mathematically analyze the invisible physics of energy capture, friction reduction, and torque multiplication. Let's begin. We begin with the absolute governing physics of rotational energy, the moment of inertia, denoted by the letter I. Look at the majestic mathematical equation on the left. I equals the integral of r squared dm. This isn't just theoretical math. This formula dictates the life or death of an automatic watch. By definition, the moment of inertia I measures the rotor's resistance to angular acceleration. Why do we want resistance? Because mechanical function depends on it. A higher moment of inertia means the rotor requires more force to start spinning, but crucially, it means it stores vastly more kinetic energy once it is moving. It acts as a heavy flywheel, plowing through resistance to deliver a sustained, powerful force to compress the mainspring. Look at the variables on the right. I is the total energy potential. R is the radius, the physical distance of the distributed mass from the central pivot. And dm is the differential mass element, the actual physical material we are using, like tungsten or gold. The key takeaway is this: moment of inertia is not just about how heavy the rotor is, it is the definitive mathematical parameter that links the physical geometry of the rotor to its actual winding performance on the wrist. Let's break down that integral equation to understand the 3 governing variables of inertia, and the scaling laws that dictate mechanical design. Variable 1 is the radius, r. This is the exponential driver. Look at the graph. Because r is squared in the governing formula, r squared, it is the single most influential design factor. A marginal, tiny increase in the rotor's outer diameter yields an explosive, exponential increase in total inertia. Watchmakers always want the widest rotor possible. Variable 2 is thickness, h. This is the linear modifier. Thickness scales linearly with inertia. If you double the thickness of the heavy sector, you exactly double the mass, and consequently, you simply double the inertia. The graph is a straight line. Variable 3 is material density, ρ. This is the volumetric multiplier. A higher density yields greater inertia for the exact same geometric volume. This allows engineers to pack maximum mass into highly restrictive spatial envelopes. The challenge? Watch designers are trapped. They must balance the desire for exponential radius gains against the strict, unforgiving constraints of the movement's diameter and the aesthetic demand for ultra-thin case thickness. They have to manipulate these 3 variables constantly. Because of those 3 variables we just discussed, we arrive at a fascinating concept: moment of inertia equivalence. This means we can achieve the exact same energy potential using radically divergent architectures. Look at the mechanical scale on the screen balancing 2 completely different rotors. On the left, we have architecture A, the micro-rotor. It has a very small radius. The constraint here is that R is strictly limited because the rotor is embedded flush within the gear train. To compensate for the severe loss of the r-squared exponential advantage, the engineer must utilize extreme thickness H and ultradense materials, like solid platinum, to claw back enough mass to generate the required inertia. On the right, we have architecture B, the full-size rotor. It has a massive radius r. The constraint here is that it must clear the entire movement, but we want the watch to remain exceptionally flat. The compensation? It leverages the maximum possible movement diameter to achieve the required inertia using a very thin, relatively light peripheral sector. The mathematical relationship between radius and mass dictates the fundamental architecture of the entire movement. I_micro can absolutely equal I_full, but the engineering paths to get there are completely opposite. Let's look at how material density optimization plays into engineering the heavy sector. We are looking at a timeline of specific gravity, measured in grams per cubic centimeter. At the low end, around 11.3, we have lead. These were historical cast materials used in early bumpers. Lead is entirely obsolete today due to toxicity, extreme softness, and deformation over time. Moving up, we hit the modern standard, sintered alloys, hovering around 19.0. These are copper-nickel matrices heavily loaded with tungsten powder. They provide incredible density at a reasonable manufacturing cost. As we cross into the luxury tier, we find 22-karat gold at 19.3. Used in high-end calibers, it combines excellent specific gravity with brand prestige and absolute corrosion resistance. Finally, at the absolute pinnacle, we have platinum at 21.4. This is the ultimate high-density material, strictly reserved for ultra-thin or micro-rotor movements where every fraction of a millimeter counts. The material imperative is absolute. To maximize inertia within a minimal volume, the outer rim must be constructed from exceptionally dense materials. The evolution of the automatic watch is directly driven by the metallurgical pursuit of packing maximum mass into restrictive spatial envelopes. We've optimized the heavy mass. Now we face a terrifying engineering problem: suspending that massive weight. This is the tribological challenge, defeating parasitic energy drain at the mechanical nexus. Look at the 360-degree structural problem on the left. Unlike historical bumper masses that were safely stabilized by a fixed upper bridge, a full-rotation modern rotor operates with zero overhead support. It relies entirely on a single, isolated central suspension point to hold it in place. Now look at the dynamic load vectors attacking this single point. We have axial loads, gravity constantly pulling the heavy tungsten mass downward, combined with severe vertical shocks from drops. We have radial loads, lateral impacts from rapid wrist movement creating violent shear forces snapping against the pivot arbor. And we have rotational torque, the active winding forces fighting to drive the gear train. The energy penalty here is severe. Rotor bearing friction acts as a direct, parasitic drain. Every single joule of energy lost to sliding friction at this central pivot is kinetic energy permanently subtracted from the mainspring. The rotor bearing must somehow resolve two inherently competing requirements: minimizing rotational friction while simultaneously maximizing extreme shock resistance. Let's look at how engineers historically tried to solve this suspension problem. Here is suspension system 1, the locking system, or VERU. This represents the baseline architecture of sliding friction. Look at the cross-section mechanism architecture. The rotor sits atop a fixed, static central axle. To keep the rotor from falling off, a spring-loaded locking clip, the VERU, slides laterally into a machined groove in the axle to provide axial retention. Now, let's analyze the diagnostic flaws of this design. First, it generates high parasitic friction. Look at the red zone in the diagram. There is constant, heavy sliding contact between the inner edge of the locking clip and the walls of the axle groove. This sliding friction acts like a brake, constantly bleeding away precious kinetic energy before it reaches the gears. Second, it suffers from structural vulnerability. To accommodate the sliding clip, the central axle must be machined exceedingly thin. This creates a severe choke point, making the axle highly susceptible to snapping cleanly in half under sudden radial shock. While mechanically simple, the VERU system suffered from unacceptable energy losses and structural fragility. Engineers recognized the fragility of the original VERU system and attempted to fix it. This led to the improved locking system architecture, aiming for iterative gains in shock resilience. Look at the original system faded on the left, with its terrifyingly thin 0.40 mm axle. Now compare it to the improved system on the right. The first engineering iteration was to massively increase the diameter of the fixed central axle, bumping it up to 0.80 mm. This drastically reduced the snapping risk. The second iteration involved the relocation of the clip. The VERU was moved from a static position hidden inside the movement to a dynamic position mounted directly on the rotor body itself, interfacing with an external groove on the thicker axle. What was the performance delta? Shock resilience was indeed massively improved due to the thicker, more robust axle geometry. However, while friction was slightly reduced by better machining, the system was fundamentally still reliant on inefficient sliding contact. Incremental geometric improvements stabilized the rotor against shock, but they completely failed to eliminate the core tribological flaw of sliding friction. We needed a paradigm shift. Before the ultimate solution was found, many high-end manufacturers utilized suspension system 2, the screw system, or système à vis. This system prioritized precision calibration and axial play, known in French as abat. Look at the construction mechanics in the diagram. The rotor pivots freely around a very robust, thick, fixed central axle. Instead of a sliding clip, a single, wide-headed retention screw is driven directly into the top of the axle, locking the rotor in place. The success of this system relies entirely on the critical calibration of the abat. The precise tighten height of that screw head dictates the vertical clearance, or play, of the rotor. If the watchmaker tightens the screw too much, the rotor binds against the axle lip, friction spikes exponentially, and the watch simply stops winding. If the screw is left too loose, the rotor wobbles excessively under shock, potentially striking and permanently scratching the beautiful, delicate movement bridges below. While this system is exceptionally robust and very easy for a watchmaker to service with a single screw removal, it still inherently relies on energy-dissipating sliding contact against the inner bore of the rotor. It was good, but not perfect. The tribological holy grail was finally achieved with suspension system 3, the ball bearing system, or polyrobills. This is the undisputed modern standard of near-zero energy drain. This represents a total tribological breakthrough. By introducing microscopic balls, engineers completely replaced energy-draining sliding friction with highly efficient rolling friction. It achieves near-zero energy loss, ensuring that virtually 100% of the harvested kinetic energy from the heavy mass actually reaches the gear train. Look at the microarchitecture in the 3D rendering. It utilizes a precision double-cone profile housing, typically containing 5 to 7 microscopic synthetic ruby or ceramic balls. These balls are held in strict, perfect alignment by a delicate metal cage, requiring absolute surgical precision during factory assembly. Furthermore, look at the shock distribution. When a watch is dropped, the multidirectional shock vectors are smoothly and instantly distributed across all the rolling elements simultaneously. This provides massive, multi-axis impact resistance without binding or snapping the axle. The ball bearing system represents the ultimate optimization, maximizing both rotational efficiency and structural durability. Let's synthesize our suspension analysis with an evolution matrix. I want you to clearly see how the drive to eliminate parasitic friction pushed successive architectures. We started with the locking clip, or veru. The friction interface was pure sliding contact between the clip and the axle. The energy loss coefficient was highly detrimental. Shock tolerance was poor due to the vulnerable thin axle, and serviceability was difficult. We moved to the screw system. The interface was still sliding, but now between the bore and the axle. Energy loss was moderate, entirely dependent on the watchmaker's skill in setting the abat clearance. Shock tolerance was high, and serviceability was excellent with just a single screw. Finally, we arrived at the ball bearing. The friction interface was revolutionized from sliding to rolling. The energy loss coefficient dropped to near zero. Shock tolerance became ultimate, with multi-axis distribution. The only minor drawback is serviceability. You cannot repair a sealed bearing, it requires specialized complete replacement. The key takeaway is clear. The entire evolutionary arc of rotor suspension was driven by a single imperative, the total eradication of sliding friction to maximize winding efficiency. Now that we have a freely spinning, highly efficient rotor, we must harness its power. This brings us to force transmission, the automatic gear train, whose job is routing and rectifying kinetic power. The primary function of this train is to seamlessly transmit the chaotic, multidirectional kinetic energy from the freely spinning rotor all the way down to the rigidly fixed ratchet wheel of the mainspring barrel. This journey happens in two distinct stages. Look at stage 1 in the red zone, the reversal section, or train de renvoi. The sole job of these gears is to redirect and rectify the geometric motion of the rotor. If the rotor spins clockwise, the output must turn right. If the rotor spins counterclockwise, the output must still turn right. It manages high-speed, low-torque kinetic input. Once direction is corrected, we enter stage 2 in the blue zone, the reduction section, or rouage réducteur. This performs the critical physical conversion of power. It systematically steps down the high rotational RPM of the rotor to radically multiply the torque output required to actually compress a thick steel mainspring. The automatic gear train is a highly specialized two-stage machine. Let's break down that transmission chain into its 4 precise functional elements. We will trace the step-by-step handoff of kinetic energy. Component 1 is the rotor pinion, the pignon de la masse oscillant. This is the absolute first point of force extraction, permanently attached and integral to the spinning rotor mass. Component 2 represents the intermediate wheels, or mobiles intermédiaires/redresseurs descends. Think of these as the direction correctors. Their job is purely geometric. They transport force across the spatial void of the movement plate and ensure the output only turns one way. Component 3 encompasses the reduction wheels, the mobiles de reduction. These are the heavy lifters of the movement. This is a sequence of successive pinions and wheels that execute the mathematical torque multiplication. They trade speed for brute force. Finally, component 4 is the ratchet wheel, the ratchet. This is the terminal output. While it is technically part of the manual winding train, it is utilized by the automatic module as its ultimate, final drive target to tension the spring. Every distinct mobile performs a mathematically precise role in this journey. Let's look closely at the mathematics of that force multiplication. I want to explain the incredible 1:110, up to 1:180 reduction ratio. Look at the conversion metric. For every single full, 360-degree rotation of the ratchet wheel, the rotor must execute between 110 and 180 complete, frantic revolutions. Why is this massive disparity necessary? It's about the strict conservation of power. Look at the input state on the left. Human wrist movements produce high-frequency, low-amplitude oscillations. Your wrist flicks fast, but with very little actual torque behind it. Now look at the output state on the right. Compressing a thick steel mainspring requires massive, sustained, crushing compressive torque. The gear train acts as the great equalizer. It trades rotational velocity for mechanical force. As the RPM drops across the reduction wheels, the torque increases proportionally. The 1:110 plus ratio mathematically proves that automatic winding is specifically engineered to thrive on the chaotic, high-frequency, low-power micromovements of your daily life. It turns nervous energy into unstoppable force. To truly understand the gears, we must realize that the gear train undergoes a fundamental state change of energy as it moves from phase 1 to phase 2. It transitions from spatial routing to physical compression. Look at phase 1 on the left, geometric routing. In bidirectional systems, these 1 to 3 intermediate wheels act as highly complex mechanical inverters. Their primary job is spatial geometry, ensuring the output gear always turns the same way, regardless of the input direction. The torque here is low, the speed is high. Now follow the arrow across the state change to phase 2 on the right, physical transformation. These reduction wheels execute the fundamental conversion of kinetic energy into potential energy. Because torque is increasing exponentially as we move toward the ratchet wheel, the final reduction pinions experience massive, tearing shear forces. To survive this, the phase 2 wheels require incredibly robust, thick axles, often supported by heavily jeweled pivots to prevent the arbors from snapping under the crushing load. The train transitions from a clever routing puzzle at the top end to a brute force torque multiplier at the bottom end. Fitting all these gears into a watch requires negotiating severe three-dimensional spatial constraints. Let's look at gear train topology, planar versus Z-axis architecture. Look at the planar footprint on the left, the top view. The automatic gear train cannot just go wherever it wants. The gears must be carefully routed radially around the perimeter to absolutely avoid conflicting with the base movement's escapement and the existing manual gear train. It is a labyrinthine exercise in 2D space management. Now look at the Z-axis stacking on the right, the axial view. This is where the real challenge lies. The automatic module is invariably mounted high above the base movement. But the ratchet wheel it needs to drive is buried deep down on the barrel arbor. The gears are not arranged end to end, they overlap vertically. Notice the strict clearance tolerances. The heavy rotor mass must swing freely above the bridges without ever striking the caseback during a shock flex. Meanwhile, microscopic steel pinions must securely bridge the vertical gap down through the stratified layers to reach the nested barrel. It is a brilliant three-dimensional mechanical puzzle. Now we arrive at a fascinating engineering debate, single-direction winding. Let's explore the core concept of unidirectional engagement and the freewheeling stroke. Look at the definition and logic. In a single direction system, the mainspring is tensioned by the rotor's rotation in one active direction only. If the rotor spins clockwise, it wins the watch. But, in the opposite direction, the rotor completely freewheels. It spins silently, rapidly, with absolutely zero mechanical resistance, winding nothing. Let's define the key terminology. The winding direction is the active stroke where the rotor rigidly couples to the gear train, forcing energy into the spring. The free direction, or sens libera, is the idle stroke where the rotor instantly decouples and flies free. Historically, this was used in Harwood's limited rotation bumpers because it was simple. However, today, it is highly optimized and deliberately utilized in some of the most premium, high-end 360-degree full rotation calibers in the world. I want you to understand that single-direction winding is not a mechanical compromise or a cost-cutting measure, it is a highly optimized, deliberate engineering architecture. We will see why on the next slide. If we are going to build a single-direction system, we face strict mechanical requirements. We must flawlessly enforce the locked and freewheeling states. This creates a binary imperative: the system demands a mechanism that achieves instant, crushing, zero-slip lockup in one direction, and completely frictionless, floating gliding in the other. There can be no in-between. Look at the core componentry in the diagram. It relies on a free wheel, or roue libre. This is a specialized gear, often featuring highly asymmetrical, aggressively angled wolf teeth, mounted on the transmission axis. Engaging this is the Paul system, or cliquette spring tension levers that interface with the free wheel. Let's trace the operating states on the graph. In the engaged state, the Paul drops deep into the tooth root, creating a solid, immovable physical link that transfers massive torque to the gear train. In the disengaged state, the Paul rides silently and smoothly over the sloped backs of the wolf teeth, breaking the mechanical transmission chain instantly. Reliable single-direction winding relies entirely on the microscopic, flawless precision of the freewheel and Paul geometry. Why would top-tier engineers actively choose to throw away half of the rotor's movement? Let's examine the engineering case for single-direction logic, efficiency, simplicity, and equilibrium. Point 1. Efficiency, or the inertial slingshot. The bidirectional problem is that the rotor wastes vital energy overcoming initial winding friction every single time it changes direction. The single-direction benefit is massive. The free stroke allows the rotor to rapidly build completely unimpeded kinetic velocity. When the wrist eventually flicks it back into the winding direction, this massive accumulated inertia slingshots the impulse into the gear train with devastating force, easily overcoming mainspring resistance. Point 2. Architectural simplicity. Eliminating complex bidirectional reversing inverters drastically lowers the overall friction of the movement, removes highly stressed mechanical failure points, and vastly simplifies servicing for the watchmaker. Point 3. Stable equilibrium, or position de repose. As you can see in the diagram, a free-swinging rotor naturally and quickly finds a stable, vertical rest state aligned with gravity. Zero energy is wasted fighting complex, dragging reversing mechanisms just to reach this natural state. Exhaustive empirical studies prove that this momentum-building free swing massively amplifies winding efficiency for real-world, erratic wearing habits. We have reached the end of set 2. Let's synthesize the interdependent physics of the rotor system before we transition into the complex mechanisms of set 3. We explored 4 critical quadrants. Q1. Inertia budgeting. We learned how mathematical shape trade-offs and exotic dense materials enable engineers to design both hidden microrotors and ultra-slim full rotors that deliver equal power. Q2. Tribological evolution. We traced the critical historical progression from fragile, dragging locking clips to the optimal, double-cone ball bearings that neutralized multi-axis shock without bleeding energy. Q3. Force transformation. We analyzed the strict 1:110 plus reduction ratio, the magic gearbox that converts chaotic, high-speed wrist kinematics into massive, sustained mainspring torque. Q4. Directional logic. We uncovered the counterintuitive brilliance of single-direction systems, which leverage raw kinetic momentum rather than fighting bidirectional reversing friction. The key takeaway is that mastering the rotor system requires the simultaneous, delicate optimization of mass inertia, bearing tribology, gear reduction math, and winding direction logic. Coming up in set 3, we will deep dive into the mechanics of single-direction Paul systems, deconstruct the complex architecture of bidirectional inverters, and understand the extreme operating tolerances demanded of these tiny reversing mechanisms. Let's move to set 3. Welcome back. We are now beginning part 3 of our deep dive into automatic winding mechanisms. This section focuses entirely on winding rectification and inverter systems. In the previous parts, we established the physics of the rotor and the mathematics of the reduction gear train. Now, we confront the most complex kinematic puzzle in the automatic watch, direction. The human wrist moves erratically, spinning the rotor clockwise and counterclockwise in completely unpredictable patterns. However, the mainspring barrel can only be wound in one single, continuous direction. How do we bridge this gap? We will examine the intricate mechanical diodes that solve this problem. First, we will look closely at single-direction kinematics, seeing exactly how pulse systems lock and freewheel. Then, we will undertake a comprehensive deconstruction of bidirectional inverters. We will classify and analyze the 3 great families of mechanical rectifiers: the cam/lever, the rocking plate, and the modern clutch wheel. Prepare to look at some of the most ingenious microengineering ever devised. Let's begin by dissecting the exact mechanics of single-direction winding, starting with the classic limited rotation architecture, the bumper movement. Look at the schematic on the screen, it maps the information architecture. Component 1 is the oscillating mass, restricted to a 120-degree arc. Component 6 is the heart of the system, the freewheel, or roue libre. It is mounted on the mass axle and features highly asymmetrical ratchet, or wolf, teeth on its periphery. Interacting with this wheel are 2 critical pawls. Component 2 is the drive pawl, or cliquette. It is rigidly attached to the swinging mass, it is the primary physical driver. Component 4 is the retention pawl, or cliquette de retenue. This is stationary, mounted directly to the bridge, it acts as the mechanical lock against reversal. Finally, components 13 and 14 are the coil bumpers safely decelerating the mass. The power gate concept here is beautiful. The freewheel and this dual pawl system function together as a purely mechanical diode. One pawl aggressively drives the system forward, while the other holds it perfectly still. Let's trace the strokes. Let's put the limited rotation mechanism into motion and trace the kinematics of the active winding stroke. Follow the red force arrows on the diagram. Step 1, initiation, the wearer moves, and the oscillating mass, 1, rotates downward in the dedicated, active winding direction. Step 2, engagement, as the mass swings, the drive pawl, 2, which is attached to it, aggressively bites deep into the steep, vertical face of the wolf teeth on the freewheel, 6. Step 3, lock and rotation, the freewheel, 6, is now rigidly locked to the mass. It is forced to rotate. Step 4, transmission, the integral pinion, 7, underneath the freewheel rotates, driving the reduction train wheels, 8 and 9. Step 5, terminal output, the multiplied force reaches the ratchet wheel, 10, pulling it forward and tensioning the mainspring. Finally, step 6, secure, the mass hits the bumper and stops. Instantly, the stationary retention pawl, 4, drops into the wolf teeth under the pressure of its spring, 5. This physically locks the entire gear train against the massive reverse torque of the mainspring, holding the gained energy. The active stroke is complete. Now, what happens when the wrist moves the other way? Let's trace the kinematics of the idle stroke, or the free direction. Follow the blue arrows. Step 1, reversal, the oscillating mass, 1, hits the bumper, reverses, and rotates in the non-winding direction. Step 2, skipping phase, look at the detail circle. The drive pawl, 2, encounters the shallow, sloped approach angle of the wolf teeth. Instead of biting, it harmlessly and silently rides up and skips over them. Step 3, isolation, because the drive pawl is skipping, the freewheel, 6, remains completely stationary. Absolute zero torque enters the reduction train. Step 4, hold, why does it stay stationary? Because the stationary retention pawl, 4, is still firmly locking the freewheel in place against any drag. Step 5, accumulation, here is the genius of the system. The heavy mass swings freely backward under near zero mechanical load. It rapidly builds immense kinetic energy and velocity without fighting the mainspring. Step 6, arrest, the mass is gently caught and decelerated by the opposite bumper spring, 14, ready to slingshot back into an active stroke. The idle stroke is not wasted motion, it actively amplifies the force of the subsequent winding stroke. Now let's examine single direction mechanics applied to a modern full rotation 360-degree mass. This is the Balladur system. It is an utterly brilliant piece of passive mechanical logic. Look at the system logic. A 360-degree unrestricted rotor cannot use fixed pawls on its axis. Instead, it utilizes a laterally shifting, floating intermediate wheel to passively sense the rotational direction. Let's identify the parts. Component 1 and 2 are the full rotation mass and its direct-driven central pinion. Component 4 is the stop wheel, or renvoi d'arrêt. This is the fixed pivot receiver that feeds the reduction train. Component 5 is the stop pawl, dictating that the stop wheel can only turn in one permitted direction. The absolute star of the show is Component 3, the Balladur, or renvoi Balladur. It is a floating intermediate wheel. It has no fixed central pivot hole. Instead, it travels laterally left and right inside an elongated, kidney-shaped cavity milled directly into the base brass plate. The Balladur is an ingenious, passive direction sensing element that physically relocates itself based purely on the rotational torque applied by the rotor. Let's see how it shifts. Let's analyze the Balladur kinematics during clockwise winding engagement. This is the active stroke. Follow the red arrows. Input, the wearer's wrist flicks, and the rotor pinion, 2, turns clockwise. Meshing force, the clockwise rotor pinion forces the floating Balladur wheel, 3, to turn counterclockwise. Now, pay attention to the physics. The specific gear meshing angles, combined with the inherent friction of the teeth rubbing together, generates a strong, lateral physical thrust vector. Shift, this lateral thrust physically shoves the entire Balladur gear, 3, across its elongated cavity until it smashes into deep mesh with the stop wheel, 4. A light return spring, 6, assists this default engagement. Drive, the stop wheel, 4, is now driven counterclockwise, which is the permitted winding direction allowed by its pawl, 5. Transmission, a perfectly rigid, locked kinematic path is formed. Force flows from the stop wheel, through the reduction wheels, 7 and 8, all the way to the ratchet, 9. Clockwise rotor torque creates a locked, unyielding kinetic bridge through the entire train. Now, the wrist flicks back. Let's analyze the Balladur kinematics during counterclockwise disengagement. This is the free stroke. Follow the blue arrows. Input, the rotor pinion, 2, violently reverses to a counterclockwise rotation. Repulsion, the instant the rotation reverses, the tooth friction and the meshing angles invert. The lateral thrust vector flips a full 180 degrees. Disconnect, this reverse thrust violently repels the floating Balladur wheel, 3. It is physically pushed away from the stop wheel, 4, sliding across its cavity and compressing the light return spring, 6. Isolation, the bridge is broken. The stop wheel, 4, is no longer being driven. It is held perfectly static by the stop pawl, 5, locking the mainspring tension. Freewheeling, because the Balladur is disconnected from the stop wheel, the entire reduction train is isolated. The heavy rotor and the little Balladur simply spin freely together in the void under ultra-low drag, building momentum. Disengagement is entirely automatic and instantaneous. Reversing the input torque inherently destroys the structural bridge. We now move from single direction to the immense complexity of bidirectional winding. This introduces the rectification problem. Look at the conceptual flow on the screen. On the input side, we have the human wrist. Wrist movements generate continuous, random, rapidly alternating clockwise and counterclockwise rotor swings. However, on the output side, the delicate reduction gear train and the massive mainspring must experience strictly unidirectional torque, or the watch will destroy itself. How do we solve this? We insert a mechanical rectifier, known in horology as the inverter, or inversor. The inverter acts exactly like an electrical full-wave rectifier diode bridge. It takes alternating, chaotic AC kinetic input and mechanically forces it into a smooth, constant direction DC output. To achieve this mechanical miracle, watchmakers over the last century have developed 3 distinct engineering paradigms. 1. The cam and lever ratchet, which provides intermittent pulsed power. 2. The rocking plate or bascule, which relies on geometric repositioning. And 3. The clutch wheel, or mobile de-embrayage, which uses reciprocal internal engagement. The inverter is the ultimate solution to kinetic rectification, but it is a nightmare of engineering compromise. Let's dissect Family 1, the cam/lever ratchet architecture. This is one of the earliest and most robust solutions to bidirectional winding. Look at the core architecture. Component 2 is an eccentric cam. It is a non-circular disc mounted off-center, directly to the rotor axle. Component 3 is the lever ratchet. This is a massive, heavy mechanical follower shaped like a claw that wraps entirely around the cam. Component 4 is the drive pawl, the active pusher. Component 5 is the retention pawl, the passive locker holding the output wheel. 7. Here is the kinematic translation. Step 1. As the rotor spins, it does not matter if it is clockwise or counterclockwise, the eccentric, off-center cam acts like a piston. It forcibly shoves the heavy lever ratchet into a violent, back-and-forth linear oscillation. Step 2. This lateral, side-to-side oscillation drives the attached pawls. As the lever rocks right, the drive pawl pushes the output wheel, 7, forward exactly 1 tooth. As it rocks left, it resets for the next push. Continuous, chaotic bidirectional rotation is mechanically translated into linear oscillation, which is then translated back into unidirectional stepped rotation. While the cam and lever ratchet system is brilliant, we must analyze its output characteristics and limitations. Look at the torque output graph on the left. Notice the energy delivery profile. The blue line represents ideal, continuous gear-driven torque. But the red line represents the cam/lever output. Energy is delivered to the reduction train in massive, discrete, intermittent spikes, rather than a smooth flow. This jerky, step-by-step motion creates discontinuous torque, or micro-stuttering, all the way down at the ratchet wheel. Let's look at the engineering trade-offs. The strengths are undeniable. It is mechanically simple, brutally robust, and highly resistant to shock because the lever and cam have massive component cross-sections. You cannot easily break them. Historically, it was incredibly significant. However, the weaknesses ultimately doomed it. It is energetically highly inefficient. Look at the design. There is extreme sliding friction occurring directly at the heavily loaded interface between the spinning cam perimeter and the inner wall of the lever ratchet follower. It bleeds kinetic energy as heat and wear. Its pulse delivery prevents it from achieving the optimal, silky smooth winding efficiency demanded by modern luxury calibers. Moving to Family 2, we introduce alternating gear engagement, specifically the simple bascule, or rocking plate. This system abandons pulsed levers for smooth, continuous gear meshing. The system logic here relies on active geometric repositioning. Look at the diagrams. An intermediate wheel, 3, sits on a floating, pivoting rocking plate, the bascule, 4. This floating wheel is always meshed with the rotor input wheel, 2. Let's trace state A, clockwise input on the left. The rotor turns CW. The rotational torque physically grabs and tilts the entire bascule to the right. Wheel 3 swings over and rigidly engages output wheel A, 5. The gear train is driven forward. Now look at state B, counterclockwise input on the right. The rotor violently reverses. This reversing torque violently tilts the bascule the completely opposite way. Wheel 3 swings left to engage output wheel B, 6. Because wheel B adds an extra gearing stage before hitting wheel 7, the final output direction at wheel 7 remains perfectly identical. The bascule acts as an active, passive direction sensor. The rotational torque of the rotor itself physically flips the gear path like a train switch to maintain unidirectional output. The simple bascule was good, but it had a flaw. During the split second the plate was swinging from left to right, the rotor was freewheeling, losing energy. Engineers solved this with the double reverser enhancement. Look at the schematic. The engineering enhancement is brilliant. It replaces the single swinging wheel with a dual array. Two continuously meshed intermediate wheels, 3 and 4, now pivot together on a single mobile platform, or Playform Mobile, 5. Let's trace the kinematic operation. Under clockwise input, the rotor turns wheel 2. The torque tilts the platform left. Wheel 3 engages and directly drives the output wheel 6. Under counterclockwise input, the rotor reverses. The platform tilts right. Now wheel 3 drives wheel 4 and wheel 4 engages and drives the output wheel 6. The output direction is flawlessly constant. What is the performance delta over the simple reverser? Because two wheels are always in mesh on the platform, torque delivery is significantly smoother. Most importantly, it drastically reduces mechanical backlash and the dead angle, the wasted rotation, during the exact millisecond of direction reversal. It is a highly refined, continuous delivery system. We now arrive at the pinnacle of modern automatic winding, Family 3, the clutch wheel mechanism, or mobile deembrayage. This represents a massive paradigm shift in horological engineering. The shift is fundamental. This system features absolutely zero floating, tilting, or swinging elements. There are no bascules. It relies entirely on fixed pivot gear arrays and internal component locking. Let's dissect the anatomy of a clutch mobile. Look at the 3D cutaway. It consists of three main parts. Part 1 is the clutch wheel. The outer perimeter features conventional gear teeth to interface with the train, but the inner perimeter features a ring of aggressively angled wolf teeth. Part 2 is the clutch pinion in the center. It receives drive from the outer wheel via those wolf teeth in one direction, but it freewheels independently in the other. Part 3 are the internal pawls. These tiny, spring-loaded claws are mounted inside the wheel, engineered to catch the pinion in one direction and skip in the other. The system relies on reciprocal logic. It utilizes two paired clutch assemblies working in direct opposition. When clutch 1 locks and drives, clutch 2 automatically freewheels. When clutch 2 locks and drives, clutch 1 freewheels. Let's see this dance in action. Let's trace the power routing of the clutch kinematics during clockwise rotor rotation. Follow the red arrows representing active force. Step 1, input, the wearer's wrist moves, and the rotor pinion, 2, rotates clockwise. Step 2, primary drive, because it's meshed, clutch wheel 1, component, 3, is driven counterclockwise. Step 3, internal lock, this is where the magic happens. As clutch wheel 1 turns CCW, the internal pawls inside it aggressively catch against the steep, vertical faces of the wolf teeth on its central clutch pinion, 4. Step 4, output, clutch pinion 1 is now locked solid to its outer wheel. It acts as a solid, rigid drive shaft, pushing the first reduction wheel, 9, in the correct winding direction. But look at what is happening simultaneously on the right side. Step 5, reciprocal freewheel, the rotor pinion is also spinning clutch wheel 2, component, 6, clockwise. However, in this direction, its internal pawls, 8, slide harmlessly and silently backwards over the shallow angle of its pinion's wolf teeth. Clutch 2 is totally decoupled from the output. In clockwise rotation, clutch 1 acts as a solid drive shaft, while clutch 2 acts as a frictionless bearing. Now, the rotor instantly snaps back the other way. Let's trace the clutch kinematics during counterclockwise rotor rotation. Follow the red active force arrows again. Step 1, input reversal, the rotor pinion, 2, violently reverses and rotates counterclockwise. Step 2, primary freewheel, clutch wheel 1, component, 3, reverses to clockwise. Instantly, its internal pawls hit the shallow angle and skip over the wolf teeth. Clutch 1 completely disengages from the drive chain. It now acts as the frictionless bearing. Step 3, secondary drive, look at the right side. Clutch wheel 2, component, 6, now rotates counterclockwise. This is the critical direction. This forces its internal pawls to lock firmly into the wolf teeth of clutch pinion 2, component, 7. Step 4, constant output, clutch pinion 2 is now the fully driven shaft. Due to the fixed geometric array of the gears, pinion 2 drives the exact same reduction wheel, 9, in the exact same winding direction as before. The key takeaway is profound: continuous, smooth, unidirectional output is maintained at all times. Notice that there are zero output anti-reverse pawls clicking against the reduction wheel. The locked clutches internally prevent any reversal of the gear train. It is perfectly silent and perfectly efficient. Because the clutch wheel system is the modern standard, engineers have relentlessly optimized its internal architecture. Let's examine 3 engineering variations of Family 3. On the left is the multi-pawl clutch. Instead of 1 or 2 pawls, it distributes 3 or more pawls evenly around the inner periphery. The advantage? Dramatically finer engagement resolution. By staggering the pawls, one is always mere microns away from locking, which minimizes the dead angle or backlash when the rotor reverses, capturing even the tiniest micro-movements of the wrist. In the center is the spring disengager clutch. Look at the cross-section. Instead of relying on individual, tiny coil springs behind each pawl, it utilizes a single, integrated flat spring plate to provide the disengaging force. The advantage is space. It eliminates bulky separate spring components, allowing for an ultra-flat movement design critical for thin dress watches. On the right is the absolute pinnacle, the roller-type clutch. It replaces rigid, clicking pawls entirely with smooth, free-floating synthetic ruby or steel rollers. When driven, the rollers wedge tightly into a narrowing ramp, locking the wheels solid. When reversed, they roll into a wider area, freeing the wheel. The advantage? Peak modern horology. It provides exceptionally low friction, absolute silence, and minimal drag torque during the high-speed freewheeling phase. To consolidate our understanding of rectification, let's review the architectural comparison matrix of the three inverter families. Family 1, the cam/lever, produces a pulsed output, requires an anti-reverse pawl, features floating lever elements, has low to medium complexity, but suffers from moderate idle drag. It is highly robust, typical of historic calibers. Family 2, the rocking plate or bascule, produces a continuous output, also requires an anti-reverse pawl, features an aggressively tilting platform, has medium complexity, but boasts low idle drag. It is a solid, reliable choice for standard automatics. Family 3, the clutch wheel, produces continuous output, crucially requires NO anti-reverse pawl due to internal locking, features NO floating elements, only fixed pivots, has medium to high mechanical complexity, and achieves very low idle drag, especially in roller variants. Synthesis note: each family represents a unique engineering compromise. The clutch wheel represents the absolute pinnacle of modern efficiency, intentionally trading a higher part count and extreme manufacturing tolerances for the holy grail, zero floating elements and minimal friction. This is why it dominates high-end modern calibers. Before we leave inverters, you must appreciate the sheer violence they endure. This is the inverter's burden. The inverter is, without question, the most mechanically stressed, abused, and tortured subassembly within any automatic movement. Look at the massive number on the screen. 10 million to 100 million. That is 10 to the 6th to 10 to the 7th power. That is the number of violent, full-load reversals a single inverter must endure every single year on an active wrist. It faces a speed variance nightmare. The rate of force application ranges from imperceptibly slow, lazy turns while reading a book, to instantaneous, high G shock pulses when clapping hands or playing golf. It faces a force variance paradox. It must delicately capture gentle, microtorques from tiny wrist twitches, while simultaneously surviving severe instantaneous macrotorques from accidental drops that try to shear its teeth off. And what is the maintenance expectation? The customer expects this highly stressed nexus to operate flawlessly for 5 to 7 years in a sealed environment without any cleaning, without the microscopic lubrication drifting, and without any adjustment. If a gear train wheel fails, the watch stops. If the inverter fails, locks up, or slips improperly, the mainspring receives zero power regardless of how much the rotor spins, and the watch slowly, silently dies. Designing an inverter that survives that burden requires navigating impossible constraints. Let's map the 9 inverter qualities to understand the ultimate engineering paradox. On the left, in blue, we have the demands for sensitivity and efficiency. The inverter needs 3. Low release torque, minimal physical energy required to switch direction. It needs 5. High idle speed without wear, parts must freewheel at thousands of RPMs without degrading. It needs 6. Low idle drag torque, it cannot bleed the kinetic energy it just harvested. And 7. It must be compact and flat to fit in the case. But on the right, in red, we have the demands for durability and robustness. It needs 1. Long service life for millions of cycles. It requires 2. Extreme shock resistance to absorb impacts without fracturing. It needs 4. Stable characteristics, spring geometry cannot drift over decades. It demands 8. Simplicity for statistical reliability, and 9. It must be cost-effective to manufacture. Here is the ultimate engineering paradox. The very qualities that make an inverter hypersensitive and efficient, like ultralight springs and microscopic, low-friction pawls, are in direct, physical conflict with the brutal mass and thickness required for shock resistance and long-term stability. The perfect inverter does not exist, it is always a masterclass in calculated compromise. This brings us to the end of part 3. Let's summarize the mastery we have achieved over the chaotic energy of the rotor. We mastered the kinematics of single-direction systems, understanding how limited rotation dual-pulse setups and full-rotation floating balladur cavities isolate the free stroke to build massive inertial momentum. We deeply analyzed bidirectional rectification, deconstructing the pulsed brute force of the cam/lever, the geometric shifting of the rocking plate, and the internal reciprocal locking elegance of the modern clutch wheel families. Finally, we defined the 9 competing operational paradoxes that threaten a system enduring 10 million cycles a year. The inverter has successfully solved the direction problem. The energy is now flowing one way. So, what is coming in part 4, our final set? The inverter solves direction, but what happens when two power sources collide? We will explore system isolation, how to disengage the manual train during automatic winding. We will uncover the overspeed danger, protecting delicate automatic gears from manual crown overdrive. We will deconstruct a masterpiece of bistable logic, the 3-arm spring. And finally, we will tackle overwinding protection, analyzing the physics of the sliding bridle pressure relief valve. Let's move to our final chapter. Welcome to Part 4, the final integration. In this last module of Chapter 8, we will explore how a fully realized automatic mechanism protects itself. We will cover disengagement, limits, and empirical validation. Up to this point, we have successfully harvested energy from the rotor and rectified it into a single direction. But a watch is not a closed system, it has 2 completely independent power sources, the automatic rotor and the manual crown. We must resolve the violent kinematic conflicts when these 2 systems collide. We will look at 1. Interface routing, handling the clash of manual and automatic input. We will examine 2. System isolation, utilizing passive mechanical logic gates like the auxiliary wheel and the brilliant 3-arm spring to decouple the trains. We will then look at 3. Boundary limits, managing the physics of surtension over winding with the sliding bridle. Finally, we will look at 4. Empirical validation, how engineers actually prove their designs work on human wrists using winding speed nomograms. A modern automatic movement is only successful if it can passively, autonomously actuate systems to protect itself against conflicting inputs and infinite energy states. Let's see how it survives. Let's clearly define the problem, the kinematic conflict of 2 independent power chains. An automatic watch is essentially a hybrid vehicle with 2 engines fighting for control. Look at the manual train parasitic drag diagram on the left. If you spin the rotor, it drives the ratchet wheel. But if the manual winding train is permanently connected to that ratchet wheel, the rotor is now forced to backdrive the sliding pinion, the crown wheel, and all those heavily greased, high-friction components. This parasitic drag would bleed off the rotor's delicate kinetic energy, severely crippling automatic winding efficiency. Now look at the far more dangerous scenario on the right, the speed multiplier hazard, or the reverse hazard. When you wind the crown manually, you inject massive, rapid torque into the ratchet wheel. The automatic train was designed to reduce speed by 1 to 180. But if you backdrive it from the ratchet wheel, that ratio inverts. It becomes a massive speed multiplier. One quick manual rotation of the crown per second translates to the microscopic automatic reduction gears being forced to spin at 6,600 to 10,800 revolutions per minute. The result is catastrophic, instant vaporization of arbor lubrication and the fracture of microteeth. Dual input winding absolutely demands strict, passive, bidirectional kinematic isolation. How do we isolate the manual train? Let's look at passive decoupling solution A, the auxiliary wheel, or renvoy auxiliar. This relies on tangential force actuation. Look at the manual mode on the left. When the user turns the crown wheel, 3, turns. Due to the angle of the teeth, the torque physically grabs and tightly pivots the small auxiliary wheel, 3, directly into deep mesh with the ratchet, 4. There is 0 slip. The manual force flows perfectly into the mainspring. The manual chain is engaged. Now look at the automatic mode on the right. The user stops winding, and the rotor takes over. The rotor drives the ratchet, 4, via its own separate pinion. As the ratchet turns, its teeth grind against the auxiliary wheel. The tangential force of the automatic-driven ratchet teeth acts like a wedge, passively pushing the auxiliary wheel outward, physically disengaging it from the ratchet. The connection is broken. The automatic train can now spin the ratchet freely without dragging the dead weight of the crown wheel and stem. Design A leverages the ratchet's own rotational force to passively flip an elegant, self-actuating kinematic switch. There is another, even more robust way to isolate the manual train. Let's look at passive decoupling solution B, axial swing disengagement, featuring the crown wheel bascule architecture. Look at the manual mode on the left. When the user twists the crown, the entire crown wheel assembly is designed to pivot slightly on an elongated axis. The manual winding torque violently forces the crown wheel to pivot tightly against the ratchet wheel, creating a secured, unyielding mesh. The mainspring is wound. Now look at the automatic mode on the right. The user lets go, and the rotor spins the ratchet. The rotation of the ratchet wheel from the rotor forces the teeth of the crown wheel backwards. This reverse pressure physically shoves the entire crown wheel to pivot away on its swinging mount, the bascule. It physically retreats from the ratchet. What is the tribological advantage here? Unlike Design A, where the teeth might still lightly brush against each other, Design B achieves total, absolute physical separation. The crown wheel teeth never brush against the ratchet during automatic winding. It guarantees zero contact friction, maximizing the rotor's efficiency. It completely severs the kinematic link by displacing the primary axis. We've isolated the manual train, but what about the catastrophic speed multiplier hazard we discussed? We must isolate the automatic train from the violent input of the manual crown. This is the reverse conflict. Look at the diagram. When the user grabs the crown and turns it manually, massive torque enters the ratchet wheel. If the automatic train is solidly connected to this ratchet, that 1:180 reduction ratio instantly inverts. The slow, powerful turn of the crown is multiplied 180 times into blinding speed. The catastrophic failure modes are terrifying. The delicate micro-reduction gears near the rotor are suddenly forced to spin at over 10,000 revolutions per minute. At these speeds, the specialized oils and greases on the arbors instantly vaporize due to friction heat. Without lubrication, the microscopic teeth clash and fracture, resulting in total module seizure. The key takeaway is absolute. To survive the user manually winding the watch, a flawless, one-way breakaway clutch mechanism must exist exactly between the final automatic drive pinion and the delicate reduction train. The connection must be severed the instant manual torque is applied. Let's look at the masterpiece that achieves this. Enter one of the most beautiful components in horology. The dual-function architecture, the 3-arm spring, or Resort 3 bras. We will look at its first job, Part 1, the automatic driver function. Look at the 3D exploded view. Component 7 is the driving wheel, powered by the rotor. Component 5 is the ratchet driving pinion, which physically turns the main ratchet, 4. Trapped between them is Component 6, the 3-arm spring. Let's observe State 1, the rigid driver. During normal automatic winding on the wrist, energy flows from the rotor into the driving wheel, 7. The 3 curved arms of the spring are preloaded to push radially outward. Under forward rotational torque, the tips of these 3 arms lock seamlessly and rigidly into 3 matching holes machined into the driving wheel. Because the arms are locked in the holes, rotational torque is transmitted rigidly from the driving wheel, through the spring, into the pinion, 5, and finally to the ratchet, winding the mainspring. In automatic mode, the 3-arm spring acts as a flawless, solid coupling device transmitting high torque without a hint of slippage. Now, the user grabs the crown and violently twists it. Let's see the 3-arm spring perform its second, life-saving job. Part 2, bistable disengagement, or the yielding function. Look at the kinematics on the left. Step 1, the reverse torque, the crown turns, driving the massive ratchet, 10. The ratchet forces the pinion, 5, to spin rapidly in reverse, relative to the normal automatic flow. Step 2, the yielding state. Here is the genius of the design. This violent reverse force pushes backwards against the tips of the 3 spring arms, 6, resting in the holes of wheel, 7. Because of their specific curve geometry, this reverse pressure causes the arms to instantly deflect inward, compressing radially toward the center. As they compress, they pop out, or delog, escaping the holes entirely. Step 3, the critical safeguard. Meanwhile, the stop pawl strictly locks the automatic reduction train, 8 and 7, rigidly in place. It cannot spin at 10,000 revolutions per minute. Because the spring arms have popped out of the holes, the pinion, 5, is now completely decoupled. It freewheels harmlessly and silently over the stationary driving wheel. The three-arm spring's torque-sensitive bistable behavior, locking under forward force and collapsing radially under reverse force, is an absolute pinnacle of mechanical elegance and safety. Let's pull everything together into an architectural synthesis, the complete 19-component system. This master schematic visualizes how all the pieces we've discussed interact in a unified architecture. Look at the color coding. Zone 1 in blue is the manual winding chain. Zone 2 in red is the automatic harvesting chain. Zone 3 in green represents the interface and dual disengagement mechanisms. Trace the flow. When the rotor spins, energy flows through the red reduction wheels, 9, through the locked three-arm spring, 6, driving the pinion, 12, to turn the ratchet, 4, and wind the watch. Meanwhile, the tangential force of the ratchet physically pushes the auxiliary wheel, 3, out of the way along isolation path A, completely severing the blue manual train to prevent drag. Conversely, if the user turns the crown, the blue manual train drives the auxiliary wheel, 3, into the ratchet, 4. The ratchet spins rapidly. This reverse torque collapses the three-arm spring, 6, forcing it to pop out of the red reduction wheel, 12, along isolation path B, completely severing the red automatic train to prevent 10,000 revolutions per minute over revving. The system autonomously harvests, rectifies, and mutually isolates two completely independent powertrains in one unified, brilliant architecture. We have successfully managed the dual inputs. But now we face a problem with the output. This is the infinite energy paradox, and we must limit automatic winding by mastering the physics of surtension. The core paradox is this: unlike a manual watch, where you wind it until it hits a hard stop and you know it's full, an automatic watch constantly, relentlessly harvests energy. As long as the watch is on a moving wrist, the rotor spins. Therefore, the mainspring theoretically faces infinite, endless tension input. It never stops being wound. Look at the diagram on the right. What are the hazards of surtension or overtension? If we do nothing, the mainspring will coil so tightly that it exceeds its elastic limit. The result is material fatigue, plastic deformation of the steel alloy, and eventually catastrophic, explosive spring breakage inside the barrel. Furthermore, there is the rebatter effect. Even before the spring breaks, the massive, excessive torque transfers violently through the gear train to the escapement. This huge burst of power causes the balance wheel to over-rotate, swinging past its maximum safe arc, and physically strike the back of the pallet fork. This causes severe knocking, erratic timekeeping, and physical damage. Automatic winding absolutely demands a fail-safe mechanical pressure relief valve to safely vent this continuous kinetic input. The solution to the infinite energy paradox is the pressure relief valve, the sliding bridle, or bride glissant. This humble strip of metal prevents the watch from destroying itself. Look at the cross-section of the barrel. Phase 1 is the outward preload. The bridle is a stiff, curved piece of spring steel attached to the very end of the mainspring. It pushes outward against the smooth inner wall of the barrel drum. Below maximum tension, the outward radial static friction of the bridle against the wall far exceeds the rotational pull of the coiling spring. The spring end remains perfectly stationary, allowing the watch to wind normally. Phase 2 is the friction threshold. As the rotor continues to pump energy into the system, the internal tension rises. Eventually, the rotational pull of the tightly coiled mainspring exactly equals, and then slightly exceeds, the static friction limit of the bridle pressing against the wall. The bridle yields. Phase 3 is the slip. The instant the threshold is crossed, the bridle violently slips a small angular distance along the drum wall. This slip instantly vents the excess energy, dropping the internal tension back down to safe limits. The bridle then grips again, ready for the next cycle. The sliding bridle elegantly transforms the static, locked mainspring barrel into a highly calibrated, dynamic slipping clutch. Designing that slip is incredibly difficult. Let's look at bridle engineering, construction, and dimensional constraints. The bridle's performance relies on stringent geometric ratios. It is a highly calibrated systemic property, not just a random piece of metal thrown into the barrel. Look at the top-down barrel drum and bridle schematic. C is the inner circumference of the barrel drum. L is the length of the sliding bridle. The golden ratio of length dictates that the bridle length, L, must be strictly, precisely 10% shorter than the drum's inner circumference, C. Therefore, L is approximately equal to 0.9 times C. Why this exact 10% shortfall? It dictates the exact preload outward force required to generate proper friction. If L is too long, there is a severe risk of the bridle ends overlapping themselves as the spring coils. This creates a rigid structural lock, completely preventing the slip, leading to catastrophic surtension and a broken spring. If L is too short, the outward radial pressure drops drastically. The friction coefficient plummets, leading to premature, constant slipping. The watch will never reach full tension, resulting in a chronically underwound watch with terrible power reserve and poor accuracy. The math must be perfect. Even with the correct length, we must control exactly how the bridle slips. This involves regulating the slip, barrel drum notches, and tribology. The problem with smooth walls: if the inside of the barrel drum is perfectly, flawlessly smooth, it provides unpredictable friction decay. Once static friction is broken and a slip starts, dynamic friction is much lower. The bridle could just continue to slide uncontrollably around and around, dumping the entire stored power reserve in seconds. The machine solution: look at the diagram. The inner drum wall is not perfectly smooth. It features evenly distributed, precisely machined notches, typically 8 of them around the perimeter. As the bridle slips, the tip of the bridle violently catches in the very next machined notch. This immediately, mechanically arrests the slide. This indexing ensures the slip stops quickly, keeping the power reserve exactly at the maximum plateau. Furthermore, look at the specialized tribology. You cannot use standard watch oil here. The extreme localized heat and shear friction of the steel bridle scraping against the brass or steel drum wall would score and destroy the metal. Watchmakers must use advanced, highly specialized braking greases, often heavy Teflon or graphite matrices, to lubricate the slide while simultaneously providing enough drag to manage the slip without destroying the wall. It is a microscopic balancing act. Let's look at the actual physics of the mainspring. We will quantify energy by observing normal winding in hysteresis on a torque diagram. Look at the graph. The x-axis is the number of turns of the barrel arbor, from 0 to 8. The y-axis is the torque delivered to the escapement, measured in Newton millimeters. The top line is the winding phase, or armage. As the rotor winds the watch from a dead stop, the torque rises on a smooth, predictable, upward curve until it reaches the maximum functional force moment required to run the watch optimally. Now look at the bottom line, the unwinding phase, or disarmage. Notice that it does not follow the same path down. The unwinding torque is significantly lower than the winding torque at any given turn. The shaded delta between these two curves is called the hysteresis gap. What is this? It represents kinetic energy permanently lost to internal sliding friction. As the hundreds of coils of the mainspring rub tightly against each other while unspooling, they bleed off energy as heat. This base diagram proves that a barrel stores and releases energy asymmetrically, experiencing expected, unavoidable parasitic friction loss. Now let's add the automatic rotor's infinite energy to the graph. We must establish dynamic limits and find the critical safety threshold. Look at the extended graph. The rotor continuously pumps energy into the system, driving the blue winding line past m_max, the maximum functional torque needed to run the watch perfectly. The watch is now in the overwinding phase. It keeps climbing until it hits the red dotted line, m_gl, or the mean slipping moment. This is the exact moment the sliding bridle breaks friction and yields. The golden constraint of automatic watch design is the ratio between m_gl and m_max. The safety threshold, m_gl, is strictly engineered to occur at 135% to 150% of the functional torque, m_max. Why this specific window? If the bridle slips below 135%, the slip is too eager. The watch constantly vents energy and never fully wins, resulting in a low power reserve. If the bridle is too stiff and slips above 150%, the internal tension is too high. The massive torque causes the balance wheel to suffer from imminent risk of recoil, knocking, and eventual component failure. The safety threshold provides a strict 35 to 50% buffer above maximum functional torque to absorb shocks before extreme stress destroys the movement. Let's zoom in on that overwinding phase to see exactly what is happening inside the barrel. This is the dynamic visualization of the sawtooth slipping profile. Look at the chaotic, jagged line at the top right of the graph. This is the reality of an automatic watch on an active wrist. Event 1 is the slip. The rotor pushes the torque past m_gl. The bridle yields and slides along the wall. Instantly, the internal torque drops dramatically as energy is vented. This is the downward spike on the graph. Event 2 is the arrest. The sliding tip of the bridle slams into the next machine notch in the drum wall, or the braking grease halts it. The slide stops. Event 3 is the re-engagement. The wearer is still moving. The rotor continues winding, immediately pumping the torque back up, and it peaks instantly back to m_gl, or it slips again. This creates a rapid, continuous sawtooth pattern. The real-world state is fascinating. While on an active wrist, the mainspring spends the vast majority of its lifespan operating entirely within this microscopic, chaotic, high-tension sawtooth plateau. It is a continuous, never-ending microscopic battle between the rotor constantly forcing input, and the bridle violently releasing friction to protect the watch. We have engineered a brilliant system on paper. But how do watch manufacturers prove it actually works on a human being? We move to empirical validation, multi-axis planetary testing. The final requirement is harsh. Perfect theoretical kinematics and beautiful gear ratios are completely irrelevant if the mechanism cannot harvest sufficient, real-world energy on a living, breathing human wrist. But human wrists are chaotic and impossible to standardize. The solution is the simulation apparatus. Look at the diagram. Manufacturers use massive, standardized planetary test devices, often called cyclotists. These machines feature multi-axis articulated arms that rotate in the X, Y, and Z axes simultaneously. You strap the fully cased watches to the ends of these arms, and the machine simulates the complex, erratic, multi-directional human arm movements over precise, repeatable durations. From this, engineers derive the universal metric, winding speed, denoted as V, or V_armage. It is calculated very simply by dividing the accrued power reserve, measured in hours, generated during the test, by the test duration, also in hours. Planetary testing translates chaotic kinetic human movement into standardized, repeatable laboratory conditions, yielding a single, hard validation metric to prove the design. Once the engineers have the raw data from the planetary tester, they need a way to quickly analyze it without doing complex math every time. They use analytical tools, specifically the winding speed nomogram. What is a nomogram? Look at the chart on the left. It is a graphical calculating device. It allows engineers to instantly determine the winding efficiency factor, V, of a newly designed movement with a simple glance, without recalculating complex formulas. Reading the chart is incredibly simple. Step 1, you run the planetary test. You plot the exact test duration on the x-axis, for example, 2 hours. Step 2, you measure how much power the watch actually stored during that time. You plot that accrued power reserve on the y-axis, for example, 6 hours of power. Step 3, you trace the lines from the x and y-axis until they intersect. That intersection point will land on, or near, a specific diagonal line. That diagonal line represents the universal winding speed, V, for that specific movement under those conditions. The nomogram elegantly translates multivariable physical testing data into a single, highly actionable performance metric. Now that we have our V number, what does it mean? We must apply pass/fail metrics to establish quality control acceptance criteria. Look at the nomogram chart. It is divided into zones. Let's start with the top left. Reject, overgeared, V greater than 3.5. If the winding speed is higher than 3.5, the watch wins too fast. The reduction ratio is too aggressive. The mainspring will be permanently overtensioned on the wrist, the bridle will slip continuously and violently, wasting massive amounts of energy, destroying the braking lubricants, and prematurely wearing out the barrel wall. Fail. Now look at the bottom right. Reject, undergeared, V less than 2.0. If the speed is below 2.0, the system is sluggish. The reduction ratio is too weak. It will not harvest enough energy for a sedentary wearer, like someone working at an office desk all day. The watch will simply run out of power and stop on the wrist. Fail. The goal is the middle path. Accept, the optimal window, V equals 2.0 to 3.5. This represents the Goldilocks zone. The gearing is sensitive enough to keep a low-activity wearer fully wound, but robust enough to handle the massive torque peaks of an active athlete without burning out the bridle. Strict adherence to this narrow window ensures universal reliability across all wearer biological profiles. As we bring this chapter to a close, let us look at the synthesis, the 4 pillars of automatic winding. An automatic mechanism is only successful when it performs 4 highly distinct physical tasks simultaneously and flawlessly. Pillar 1, Harvest. The unrestricted 360-degree oscillating mass must capture multi-directional kinetic energy from chaotic, unpredictable human motion. It must maximize inertia while surviving brutal impacts. Pillar 2, Rectify. The delicate inverters, whether cam, bascule, or clutch, must force that erratic bidirectional input into a smooth, unidirectional torque, amplifying it through the reduction train up to 180 times. Pillar 3, Isolate. The system must protect itself from its user. Tangential gears and bistable springs like the 3-arm spring act as passive, autonomous logic gates, seamlessly decoupling conflicting gear trains the instant the manual crown is turned, preventing catastrophic over-revving. Pillar 4, Protect. Finally, the sliding bridle enforces strict mathematical pressure limits, safely venting the infinite kinetic energy of the rotor to prevent the mainspring from snapping and the escapement from knocking. If any one of these 4 pillars fails, the entire watch dies. We have reached the end of Chapter 8. I want to leave you with a final thought on the triumph of passive mechanical intelligence. Look at the glowing schematic on the screen. An automatic watch transcends basic power generation. It is not just a spring and a weight. It acts, fundamentally, as a self-contained mechanical computer. Consider what it does. Without a single electronic sensor, without a microchip, without a battery, and without any user intervention, it dynamically senses directional shifts in gravity and acceleration. It physically evaluates internal torque thresholds. It autonomously routes power through isolated kinematic channels depending on the input source. And it automatically vents excess physical pressure to save its own life. It achieves all of this passive computation relying entirely on physical geometry, specified material inertia, and advanced tribology. And it does it while withstanding tens of millions of violent load reversals, strapped to a swinging human arm, sealed in a metal box for decades. The modern automatic winding mechanism does not just power a watch, it represents the absolute pinnacle of autonomous, self-regulating micromechanical engineering. Thank you for your attention, and I will see you in the next chapter.